discussion about alcohols, but now we're going to focus in on some special characteristics that we sometimes encounter with them. And one of them is the need to protect an alcohol for a couple different reasons. One of them, which we've seen before, and another, which I'll introduce today. And the idea here is that the alcohol is somewhat reactive in many situations. So we have to overcome that potential side reaction or undesirable reaction, and we do that through protection. So in our notes, we could write, done to overcome incompatibility that might arise by protecting the interfering functional group. Because that hydrogen on the alcohol group is acidic enough, you can't form a Grignard reagent with the alcohol, because the magnesium, instead of inserting itself between the carbon and the bromine, it's actually just going to react with that hydrogen right there. So you will not get the desired product. What we need to do is we protect that alcohol by blocking it with some unreactive group. So with the formation of a protecting group to block that interference. And then later on, you just remove that protecting group. So the protecting group is removed later after, in this case, the Grignard reagent has been utilized. Now, this bullet is just for the specific situation of forming a Grignard reagent that will be used later in the process. But it could be many different reactions that are something you want to do. So one common way to protect an alcohol is with a trimethylsilyl group, and you use chlorotrimethylsilane to do that. So you react the alcohol with chlorotrimethylsilane in the presence of a base, and it yields what we call a TMS ether, where a TMS is just an abbreviation for trimethylsilane. Okay, so here's what happens. You have the alcohol, and the oxygen acts as a nucleophile on the silicon, and the chlorine on the TMS chloride acts as the leaving group, and then the base just comes along and grabs the hydrogen. Okay, and so what you do is you end up replacing that hydrogen with the TMS group, the trimethylsilane group. And here's a specific example: cyclohexanol. If you react it with TMS chloride, you do it in the presence of a base, you just replace the hydrogen with the TMS group. And as you can see, a lot of times that's just abbreviated because these atoms, it doesn't really matter what they are. What matters most is that they are protecting the alcohol functional group for what is to come next. So the other important thing to know about doing this is that it lowers the boiling point of the compound, because you're removing that hydrogen, which was the cause of hydrogen bonding, which of course, elevates the boiling point. So it makes it easier to get it into the gas phase, and therefore it makes it easier to analyze by gas chromatography. So again, this OH group engages in hydrogen bonding, which elevates the boiling point of this material. So if I replace that with something other than hydrogen, it can no longer engage in hydrogen bonding. And so that's going to lower the boiling point. And in many situations, you need that specifically for analyzing the compound in gas chromatography. So here is an example of a GC mass spec. The GC stands for gas chromatography. That part occurs in this oven right here. What it does is it's a technique that separates out components of mixtures based on their boiling point. And we're actually going to use this technique later in the semester. But many alcohols will not even convert into the gaseous phase in gas chromatography. And so what we do is you change the alcohols and sometimes other functional groups into functional groups that don't have the hydrogen bonding, so that they can more easily go into the gaseous phase, and therefore it will work. This analytical technique will work. And this is actually something that I have some experience with in the Navy when I worked at the Navy drug testing laboratories. If we were looking for the metabolites of cocaine in urine, so these are the major metabolites of cocaine that would be found in urine. And you can see in the one that we analyzed was this one, benzoylecgonine, but also the ecgonine methyl ester. You've got these hydrogens right there and right there that engage in hydrogen bonding. And so in order for us to analyze these metabolites via gas chromatography, we need to remove those hydrogens and replace them with trimethylsilyl group, because that, again, it protects that functional group, but it also lowers that boiling point so that we can analyze it by gas chromatography. And this example is also not in your handout, but it just once again illustrates the purpose for protecting the alcohol. So if you react this alcohol, it's got the bromine on the other side of the molecule and the alcohol group right here. And so it will react with the TMS chloride in the presence of a base, and it removes the hydrogen and substitutes it with the trimethylsilyl. So now it is protected. So before, we could not form a Grignard reagent out of this starting material because the magnesium would react with the hydrogen instead of reacting by inserting itself between the carbon and the bromine. But now with this TMS protecting group on there, I can use it to make a Grignard reagent. So I subject this to magnesium, and what I get is the magnesium inserting itself between the carbon and the bromine to get the Grignard reagent. And so then we could do a Grignard reaction. And there are many different types of Grignard reactions, but the point is that you can now exploit the fact that this carbon right here that's attached to the magnesium behaves as a nucleophile and will attack an electrophile like a carbonyl group. So that's what's going on here. This carbon, this carbon is the nucleophile, that carbon is the electrophile, and you're forming that bond. Okay, you're forming that bond right there. Okay, and then later, whenever you're done with that Grignard reaction, after you've worked it up with do the acid workup, it turns out you can really kind of do this in a single step. This acid workup does two things. It will put the hydrogen on the negatively charged oxygen, as we've seen before, but also it removes the trimethylsilyl protecting group and replaces the hydrogen, and so you get your alcohol back. So this is just a good example of how you might protect an alcohol so that you can do reactions down the line. Okay, so now we're going to shift gears a little bit and start talking about the reactions of phenols. Remember, that's a benzene ring with a hydroxyl group. And one thing that we have learned about the hydroxyl group on a benzene ring is that it activates it. So you get easily electrophilic aromatic substitution on a phenol. And again, that's because the hydroxyl group, the OH group, is strongly activating. And so other substitution reactions might occur relatively easy, like halogenation. If you wanted to put a chlorine or bromine or something on the benzene ring, that goes well. If you wanted to put a nitro group, that's what we would do with nitration. If you want to put a sulfonic acid group on there, or even like a Friedel-Crafts reaction. All of those substitution reactions will occur faster on a phenol than it will on a normal benzene ring. Something else that's important with regard to phenols is that we can oxidize them. And when you do, you get a compound called benzoquinone. So here's just a diagram of that. And like other alcohols, we can just use an oxidizing agent that has a metal in a high oxidation state. Okay, so these chromiums are in a high oxidation state. So they can take on electrons, allowing something else to dump their electrons, be oxidized. Okay, and in this case, the product is benzoquinone. And we could go on to reduce the benzoquinone with any reducing agents that we might want. Now we're going to move into talking about the spectroscopy of alcohols and phenols, specifically the IR and the NMR. So with the IR, alcohols and phenols have some important characteristic peaks that show up in the IR. One of them is the stretching peak between the carbon and the oxygen in the alcohol functional group. And that happens at around 1050 wave numbers, or inverse centimeters, however you want to say it. But the more characteristic one is the broad peak that you see between 3300 and 3600. And that's from the OH stretch. And that's very characteristic of an alcohol. So here's an example. This is cyclohexanol. It's IR. And the CO stretch is right here at about 1050. But you might not notice it as much because it's in here with a lot of other peaks. And so it may not stand out as much. The real characteristic one with alcohols is this OH peak. So look for that. That's good evidence that you have an alcohol if you see that. Okay, so we can even ask a question that will help us to figure out how to use IR to detect the presence or absence of alcohols. So let's say that I'm doing a transformation of cholesterol, which is an alcohol, into 5-cholestine-3-one, a ketone. So we're oxidizing this alcohol into a ketone. And how do we know if the reaction worked? Well, one thing you can do is you can run an IR spectrum of your product. And if you see the OH stretch in the spectrum, then the reaction didn't work. Maybe something went wrong, because you would see that broad peak between 3300 and 3600 from the alcohol, from the OH. But if you did see that carbonyl stretch, the C double bond O stretch at around 1715, that's the evidence that you're looking for, that you converted the OH into the carbonyl, the C double bond O, okay? Okay, so that's IR. So now let's talk a little bit about NMR. And alcohols do show some characteristic peaks in NMR as well. So one thing to remember is that because oxygen is electronegative, it downshifts, it shifts peaks for the hydrogens downfield because it is electron withdrawing, which causes deshielding. Okay, another important thing is that you usually don't observe any splitting between the hydrogen on the oxygen and neighbors. So spin-spin splitting is not usually observed between OH proton and neighboring protons on carbon. Another way of saying that is that, you know, the OH peak itself is always going to be a singlet, and the hydrogens on the neighboring carbons will not be split by the hydrogen on the oxygen. So here's an example of that. This is propyl alcohol. So it's color-coded, which helps us figure out which peak is what. And each of these peaks that are a little higher on the spectrum here, those are just zoomed in. So we'll start with the blue. We'll start with the methyl group here, the CH3. So here's the peak for the methyl group. And if we zoom in, we see that it's a triplet. Now remember what that means. That means it has N+1 neighboring hydrogens. So there are 2 hydrogens on its neighbor. So here's its neighbor, and indeed it has 2 hydrogens. Okay, so that's why it's a triplet. And so then we move down to the green hydrogens, right? That's the CH2 group, the methylene group, all right? And so it has 5 neighboring hydrogens, 3 on this carbon, 2 more on this carbon, so a total of 5. And that's what we see. This peak for the methylene group, color-coded with green, is a sextet. 1, 2, 3, 4, 5, 6. 5 plus 1 is 6. So 5 neighboring hydrogens plus 1 is 6. So it did split into 6 peaks. Okay, so then the magenta, this is the methylene group right here, the CH2. So it has a neighbor with 2 hydrogens on it, but it also has a neighbor oxygen with 1 hydrogen on it. But remember that this hydrogen on the oxygen will not cause splitting on its neighbors. So this magenta color-coded hydrogen is only going to experience splitting from the hydrogens on this carbon, so the 2 green ones. So it's going to exhibit itself as a triplet, 2 plus 1. And so that's what we see. It splits into a triplet. All right. And then finally, the alcohol hydrogen itself is a singlet, as we said before, because even though its neighbor has 2 hydrogens on it, the hydrogen on an alcohol does not cause splitting and it does not experience splitting. And so it shows up as a singlet. And this is actually a little bit different than what I'm used to. What I see most of the time is a broad peak as well. So instead of a nice sharp peak like this, what we will often see is it's more broadened, so it's more of a curve, something like that. Okay, maybe not that extreme, but OH peaks are typically broader than hydrogens that are on carbons. Okay, so now we're done talking about alcohols. Let's talk a little bit about ethers. And so once again, if we think about what the difference between alcohol and an ether is, we start with a water molecule. These are both derivatives of water. You could say that they're both derivatives of water. And instead of HOH, for an alcohol, we substitute one of the hydrogens with an R group, but with an ether, we substitute both hydrogens on a water molecule with an R group. And they don't necessarily have to be the same R group. How to form ethers? Well, we talked about this in Organic 1. We're going to review it now. But one popular way to make an ether is to do something called Williamson ether synthesis. And it is a reaction of an alkoxide, okay, with a primary alkyl halide and or a tosylate. I'm going to show you what that is, remind you what that is in just a second. And the mechanism is it's an SN2 reaction. Okay, so just as a reminder, this is what we mean by a tosyl group or a tosylate. And what you need to remember about it is that like a halogen, like chloride or bromide, it's a good leaving group. And so you can get this type of reaction if this is the substituent on a carbon, just like if it were a chlorine or a bromine, but it would just serve as a good leading group. That's the point. We said that this involves the reaction of an alkoxide. So, well, first of all, remember what that is. An alkoxide is when we had an alcohol, so we had ROH, okay, and then some strong base comes along and removes that hydrogen, dumps its electrons onto the oxygen, and our product is that oxygen that now has a negative charge on it. That is an alkoxide. So how do we make that alkoxide? Well, we start with the alcohol, and we react it with a strong base, pardon me, such as sodium hydride. So here's just an example reaction where we have the alcohol, react it with sodium hydride. The hydride is the nucleophile or the base. It takes away this hydrogen, okay? And so we create the alkoxide, and then the other product, of course, is just, we have, here's the sodium ion. That's where the sodium ion ends up, and then the other product would just be a bubble of H2 gas. Right? And then that alkoxide does a SN2 reaction with this primary alkyl halide. The halide serves as the leaving group, okay? And so our other product here would just be the sodium iodide, okay? So that's how you make ether. So let's review how we break an ether apart. This is the most common reaction talked about with regard to ethers, how to split them into two pieces. And we do that with a strong halo acid. So they're cleaved by strong halo acids. So you take an ether and you just essentially boil it. Remember, that's what reflux means. You reach the boiling point with a condenser, so it doesn't all boil away. But you reach the boiling point with the strong acid, and it breaks it apart into its alcohol and the alkyl halide. And the principle here is that how do you know which side becomes the alcohol versus the alkyl halide? Well, the alkyl halide forms on the less hindered side. So we'll show you an example, and then we'll come back to the previous example to show how that thumb rule applies to that situation as well. But in this example, we have, if you look, this is a primary carbon, right? It's attached to only one other carbon and two hydrogens, whereas this is a secondary carbon. It's attached to two other carbons and a hydrogen. So the less hindered side is the primary, right? And so that's why it ends up with the halogen. And then the other side ends up with the alcohol functional group, okay? So the alcohol group goes on the more hindered side, the halogen goes on the less hindered side. So again, this right here is a primary carbon, but this one is a little different. It's not a tertiary it's not a secondary or tertiary carbon, but it's an sp2 hybridized carbon. And it is also not possible to undergo, an SN2 reaction. Because remember, to undergo an SN2 reaction, you have to have an sp3 hybridized carbon. So because this one is sp2 hybridized, it cannot undergo the SN2 reaction. And so it's definitely going to end up as the alcohol, and then the other side will end up as the alkyl halide. Okay, so take a minute to predict what you think the products are going to be. Let me give you a little hint here. So, this, if you look at it, is a primary carbon, and this right here is a tertiary carbon. So the two products are this T-butyl alcohol and chloroethane. So let's take it a step further and talk about cyclic ethers. So a couple things you want to know about them is, first of all, they behave pretty much like other ethers, like acyclic ethers. Those that are not part of a ring. And because ethers are pretty neutral and pretty unreactive, inert, we often use them as solvents. So this one right here is a solvent that we've referenced several times, tetrahydrofuran. We've abbreviated that just with the THF, but that's a pretty common organic solvent. All right, and then there's the special class of cyclic ethers that we're going to introduce. They're called crown ethers, and it's actually a polyether. You have multiple ether functional groups in the ring. So, in this case, we have 1, 2, 3, 4, 5, 6. 6 ether functional groups. And the reason why they're important is because they have been found to be useful for trapping specific metal cations in that cavity. So you can see from this, this diagram right here, which shows the electron distribution, that you create this really negatively charged area in that ring. And so they'll be attracted to, metal cations and act as kind of like a trap for metal cation. So, whatever the metal might be, it's going to have, if it's a cation, it's got some sort of positive charge. And so the lone pairs of electrons on these oxygens all interact with that positive charge and trap the metal ion in that cavity. So one thing I want you to know is how to name crown ethers, because their naming convention is a little bit different. So they all follow this format, where it's a number, dash, crown, dash, other number, and then the word ether, where the first number, X, is just the total number of atoms in the ring. And then the second number, Y, is the number specifically of oxygen atoms in the ring. So that's why this one that you see in the picture is called 18 crown 6 ether, because there's 18 atoms in the ring altogether. And as we already saw, there are 6 oxygens. So it's called 18 crown 6 ether. All right, and so what you want to know about this is that it greatly improves the solubility of ionic compounds that are in non-polar solvents. Many times you might need to get an ionic compound to dissolve in a non-polar solvent. Well, that's not going to happen unless you do something to make it happen. And one technique you could try is to also incorporate a crown ether into the mixture. And so, for example, if you needed to dissolve something like potassium permanganate in toluene, potassium might fit nicely into that cavity and would help to dissolve this very polar, an ionic compound into a non-polar solvent like toluene.